Hello. I just wanted to make a quick video to finish up the first slideshow and then talk about transitioning into the last one to get you all ready for your test next Friday. Hopefully, you all have been reading the chapter and working through the homework. I haven't gotten any questions yet, but I haven't checked my email today, but I'll be checking that after this video. And of course, we have more videos to come. It's not quite over yet, but we're close to the end, so hold on there. Okay, first let's talk about what a specific heat is. A specific heat is the amount of energy it takes to raise 1 kilogram of a specific material up 1 degree Celsius. So it's the amount of heat that needs to be transferred into 1 kilogram of a material in order to increase the temperature of that material by 1 degree Celsius. On slide number 18, you see a list of common specific heats, but first I want to talk really quickly about the units. So if you look up towards the top of the slideshow where it says substance and then to the right of it, it says joule per kilogram degree Celsius. So that is the unit of specific heat. It's joule per kilogram degree Celsius. Or if you want to be more specific, joule per kilogram per degree Celsius, right? So you have to add 1 joule of energy, or excuse me, you have to add a specific amount of energy, some amount of joules, to 1 kilogram of this material to raise it 1 degree Celsius. And the most common one that we'll be using in this class, and the only one that I hope that you not necessarily remember, but keep in the back of your head or in your notes, is the specific heat of water. So when water is in a liquid state at room temperature approximately, or not necessarily room temperature, I'm sorry. When water is at atmospheric pressure, there you go, that's what I meant. It takes 4,186 joules per degree to raise it up 1 Celsius. And so you can use that 4186 as that number. Sometimes people just round it up to 4190, and sometimes in your homework will say use specific heat of 4180 for water, and either one of those work, but the 4186 is a more specific heat for water. But then if you look at the rest of the materials on the list, you'll notice that it takes less energy for most of them to raise them up a degree Celsius. For instance, look at methyl alcohol, which is right below the water. It takes 2,550 approximately joules for each kilogram to raise it 1 degree Celsius. And what this means is that since it takes less energy to increase the temperature of methyl alcohol will heat up faster. It will increase in temperature more quickly, given the same amount of energy. There's also more objects on the list. What you'll notice is if you look towards the bottom, we have objects like lead, gold, mercury, silver, copper, iron. What you will find is that metals often have much lower specific heats, and that's part of the property of metal and its conductivity. Aluminum has a specific heat of 900, which is very high for a metal. You know, we've got things like gold with a specific heat of 130 joules per kilogram degree Celsius. So if you look on the next slide, it says two materials are exposed to the same amount of heat. The first reaches a temperature of 80 degrees Celsius faster than the second. What can you infer about the specific heat of the first material? Well, since it reaches its temperature faster given the same amount of heat energy, that tells us that the first object has a smaller specific heat. So smaller specific heat means that you're quote unquote easier to increase the temperature of, given the amount of energy, your temperature will increase more. Okay, so now that we understand the idea of specific heat, we can look back at that Q equals mc delta T equation that's on slide number 18. So it says the Q, the energy, equals the mass of the material, so how much of whatever it is we have, times the specific heat, which as we said is the amount of energy required to increase the temperature of 1 kilogram of the material 1 degree Celsius, and then we have the change in temperature, which is delta T. And of course, we'll want to report those temperatures in the Celsius scale. So using this, we can find the amount of energy that is required to change the temperature of a material a certain amount. Or we can find the change of energy if we know how much the temperature changes. So Q equals mc delta T is going to be our equation that we'll be using for this portion. And of course, I'm sure you had already gleaned that from the reading and looking over the slideshow. Okay, on page 20 it says putting it all together. But before we put it all together, we got to talk about the first two laws of thermodynamics. Of course, the first law of thermodynamics says that energy can neither be created nor can it be destroyed. And also the work energy theorem, which is part of that. And the second law of thermodynamics has a lot of parts to it, but one of the parts says that two systems in contact with each other will reach thermal equilibrium. And thermal equilibrium is when two systems have reached the same temperature. When two systems or two objects in contact with each other have reached the same temperature. Right, so that means that all of the particles of the objects have the same average energy. Since we know that any two objects or any two systems in contact will eventually reach thermal equilibrium, that is, having the same temperature, we can start doing a lot of stuff with it. So conservation of energy is super helpful here. So look at this first equation that you'll see on slide 20. It says delta Q sub 1 plus delta Q sub 2 equals 0. And so what that means is that the change in the energy, or heat energy if you will, of object 1 plus the change in heat energy of object 2 will equal 0 if they've reached thermal equilibrium. So that's delta Q sub 1 plus delta Q sub 2 equals 0 if they've reached thermal equilibrium. And of course, we know that delta Q1 equals mc delta T1 and delta Q2 equals mc delta T2. And so we can expand that out as I've done on the second line where it says mc delta T1 plus mc delta T2 equals 0. So using this, we can find a lot of information if we have two objects that have reached thermal equilibrium. Because remember, first, we know that delta T, the change in temperature, is going to be equal to the final temperature minus the initial temperature. Right? That's what delta T or delta X or delta anything means. It's the final T minus the initial T. That's delta T. And since we know both object 1 and object 2, because they're in thermal equilibrium, will have the same final temperature, that means that we have most of the variables in there most of the time. If we know how much of an object we have, we know the specific heats, we can maybe find the initial temperatures if we need to. So if you haven't already started looking at that on the homework, I think there are quite a few of the questions like that. So start looking at those. Of course, I'll be making additional videos. I'll be making hint sheets that have explanations for how to work all the homework. So just keep working, guys. We're almost done. Email me with questions, of course. Thank you. You all have a nice afternoon.